Welcome everyone. I hope you're having a spectacular day and you enjoyed the keynote. My name is Hamza. I design solutions for smart manufacturing and connected vehicle use cases at MongoDB. So my background is from the industry. And when I came to MongoDB, my role has been to work with our largest manufacturing and automotive clients and actually see how we can power or enable their smart manufacturing, digital manufacturing, Industry 4.0 vision to life, and what kind of MongoDB technologies we can use to really supercharge their journey. So one of the use cases that I've been working on even before I joined MongoDB since 7-8 years ago is on predictive maintenance. How do you enable a maintenance excellence program for an organization? And then when GenAI came up, I thought to myself, where can this be applied in a traditional predictive maintenance or maintenance excellence programs, right? So today we're going to talk about GenAI powered predictive maintenance software. And we are actually going to use all the nice technological features that MongoDB Atlas has to offer and build one here. So I'm going to show you some demo snippets along the way. But if you're not from the manufacturing or automotive world, there's nothing to worry. The concepts that I'm going to talk about here today can be applied to other industries as well. Whether you're healthcare, retail, media, doesn't matter. You can use these concepts. So with that, let's get started. So I put together a little agenda. It's pretty straightforward. We'll start by looking at MongoDB's footprint in the manufacturing industry. Then we're going to look at what a maintenance excellence program actually is. How do you set it up? And then we'll see step-by-step process on how do you build one with MongoDB. All right. So when it comes to the manufacturing and automotive industry, we are generating value for our clients throughout the value chain. Our clients use us for use cases in supply chain such as inventory management, track and trace, logistics optimization, all the way to the factory use cases as well, where you're actually building these products, you're building these cars, and whether it's about predictive maintenance or unified namespace, connected workforce, or even some of our clients are building digital twin of their robots and their production equipment using MongoDB Atlas technology. Then once the product is being built and it's out of the door of the factory, all of the customers' 360 applications, all of the sales and marketing applications, we play a strong role there. And then finally, when the products are out in the field, whether it's a connected car application or a connected appliance application, you look at all the different names that we have public stories with, we are helping them build these connected customer experience, connected vehicle experience, connected products experience, fleet management experience, and so on. So in this session, we will focus on predictive maintenance use case. And some of the customers that we have public stories with are listed here. It really shows our huge footprint in the automotive and manufacturing industry. And we are privileged to be providing tangible value to our clients around the globe. All right. So COVID made organizations realize that they really need to perform a tech-driven transformation. In the past 2 years or 3 years now, manufacturing organizations have made massive strides towards digitalization. In every analyst survey that you can find, we'll find that majority of the organizations around the world already have a digital and AI transformation strategy underway. The challenge, of course, is that a lot of these initiatives are not resulting in fruitful or expected outcomes. The cost savings are not being realized, the revenue lift is not increasing. In fact, in some situations, in some of the organizations, it's getting worse over time. But having said that, the organizations that are truly successful in their transformation journey have 5 traits in common. First, they really identify the value drivers, or if they are looking at AI transformation journey, they really identify the AI value drivers that will bring them the most impact. Maintenance excellence is one such value driver that we will dig deep into this session. The second thing they do is align their AI strategy with their data strategy. As we'll see later, the AI application is as good as the data provided for training and testing and inference. This stands true for GenAI applications as well. Additionally, they will continuously enrich their data and make it easy to consume across the organization. I was working with a client from one of the largest automotive OEMs in the world, and they said the first challenge is to figure out what data we need. The second challenge is to constantly enrich this data, because you cannot really use all of the raw data for every single use case. You have to constantly enrich, transform this data, make it applicable to the different applications you want to build. So on top of enriching the data, you need to also ensure capability development. How will your people, your developers, how will you manage their productivity? How will you increase their productivity so that they can really make use of these application development tools that you're giving them, the AI tools that you're giving them? And finally, if you have set up everything correctly, you enable your whole organization to leverage the AI at pace. Without going through these successful traits, it's very hard to really realize the true potential of your AI transformation journey. So let's look into one of such impactful value driver, which is maintenance excellence or maintenance strategy creation. Having a robust AI-based maintenance strategy can yield significant revenue and savings for an organization. To start with, you actually select the equipment that is most critical to your factory operations. And any downtime on that particular equipment, machine or robot, can result in bottlenecks, and your factory throughput will be effective. So you have a factory, let's say, that is producing gearboxes, and you have a bunch of machines there in a line, and then if one of the machine goes down, your whole production line gets affected, and that machine is the bottleneck. So you have to identify that machine first. Then you have to put in sensors on the machine, and you do condition monitoring, and you figure out if there's an anomaly in their machine data. And you really look at all the subsystems of the machine to figure out if something is going wrong or something will go wrong. Once you know that there's a failure impending, then you generate your maintenance execution work order. And that's the third step. So you really need to look at your schedule, you need to look at spare parts inventory, you need to look at resources available. Do you need to fly down an expert to do it or not, or can you do it yourself? Do you have the skills available? Do you have the spare parts available to do the repair of the equipment in time before it fails? And then if you do it correctly, then you can optimally manage your spare parts as well. So this whole cycle of activities yield tangible benefits. The cost savings are realized because you are doing man-hour savings, and machine life is increased. And the revenue is increased because your machines are performing at optimal rates. So there are tangible benefits associated with AI-powered maintenance strategy. So what exactly is an optimal maintenance strategy? It is critical to select the appropriate mix of different maintenance strategies depending on the type of equipment that you have and type of production operations that you are running. So at the bottom, we have what we call reactive or breakdown maintenance. And this works like you only do maintenance on an equipment when it fails. Then we have some preventive maintenance strategies such as time-based maintenance or usage-based maintenance, where you carry out maintenance activities either at predefined time or usage of an equipment. The problem is that a machine condition changes over time, and there can be variability due to changes in process or materials. Machines are complicated, complex systems, and their failure modes may evolve over time. So these thresholds for time and usage based when I have to perform the maintenance have to be adjusted all the time. Above that, we actually have condition-based maintenance, where you actually put in sensors, you are constantly monitoring condition and determining intervention. And it's better than doing threshold or usage-based. And then on top of that, we have predictive maintenance, which actually allows you to predict failures and root causes of those failures as well before it happens. As you can guess, this is the most complex or time-consuming and requires the most upfront investment to implement predictive maintenance. So you really need to figure out which equipment to select for the predictive maintenance program. So basically, what predictive maintenance will do is it will help maintenance to be performed at the most optimal time in the most efficient way possible and increase machine reliability. Because your equipment health will deteriorate over time, and you need to perform maintenance just before the failure occurs. You don't want to let it go to the failure and do breakdown. You need to find the most optimal time before the failure occurs so you can perform maintenance in time and keep your machine and your operations running. And implementing predictive maintenance has its benefits. Some of them I've listed here. Of course, they will vary depending on the type of equipment, depending on the type of production operation running, so we can just take them as a guide. If you remember at the start, we said that if we identify an impactful value driver and a use case, and make it part of your digitization strategy, then you will get tangible results, such as decrease in maintenance cost, such as increase in productivity, decrease in unplanned stops, and also overall production or productivity improvement of your operators, technicians, and so on. So there are actual tangible benefits that a lot of companies who have implemented these solutions have found out, and they are available in analyst surveys and by consulting firms analysis as well. Right. So as with any other technological concept, predictive maintenance capabilities have evolved over time. We always had threshold-based analytics where you have a sensor, it is sending you some values, and you are looking at a predefined thresholds, and if it exceeds that value for a certain number of cycles or time, then you trigger an alert. Oh, there's something going wrong, there's a drift observed, go and check out the equipment. We also tried mathematical models or physics-based systems to actually forecast equipment behavior. These can be very complex for complicated equipment. Companies have been using fit-for-purpose machine learning models that work well for failure prediction and root cause diagnostics. So you have ML model such as decision tree classifier, or you have random forest, and you train it using run to failure data, historical data, and then you can use your test data it will tell you whether there's something going wrong or not. But the trend that I'm seeing in the market is this trend towards an automated strategy creation, where you not just predict failures, but you also generate a repair plan to fix the equipment in time. Notice that I'm using the word generate here, and we're going to see later, can generative AI help us in achieving this version 4.0 of which is the future of predictive maintenance. Because in this version, we really need deep industry knowledge. We really need access to the relevant data. We need both structured and unstructured data, you will see later. We have to bring it all together and then feed it into the system so that it can give us that whole strategy from start to finish. And for this version, there are challenges at each stage of the implementation. Now at this point, I want you to imagine a factory that has a lot of automated and manual equipment. Let's say this factory is producing gearboxes. I'll just call it ABC Gearboxes Incorporated. So this factory has a bunch of cutting machines, a bunch of milling machines, and a bunch of measurement machines, and so on. So as the general manager of this factory, I have certain budget to perform my predictive maintenance program, certain budget to invest in this maintenance excellency program. So the first question I need to answer to myself is which machine or set of machines should I prioritize for this predictive maintenance project and why? I will most probably ask my maintenance leaders or seasoned technicians. They will give me analysis done based on their experience. And I will also need to get some quantitative analysis done, because even if an equipment is failing over and over again, but the failure pattern is recognizable, you can just do usage-based or time-based maintenance for some time. You don't need to upfront invest so much into predictive maintenance project. So this is a very manual process. Once I've identified the machines that I'm going to prioritize for predictive maintenance, then I need to put in sensors on the machine, and I need to train the machine learning model using the run-to-failure data or the data coming in from the sensors. So there are two problems here. One, that I might not have enough run-to-failure data to train the machine learning model. And number two, the machine health, we talked about this before, deteriorates over time. So the failure modes may also change over time. And the data that I collect today may not be as relevant or as accurate sometime later in the future. So let's say by some miracle I get this done as well. The third thing I need to do, and this is a very, very manual process and a real pain, is that if I know that my machine is going to fail, how do I automatically generate a full-on repair plan, an optimal maintenance repair plan? Because my production operations are happening 24/7, 7 days a week, and I really need to take in all the different data silos that are available, such as inventory data, resource availability data. I need to take into account the cost of repairing an equipment, or just we need to compare it whether I just want to change it or repair it. So I want to bring all of this together and generate a repair plan. Finally, I need to make sure that I provide proper guidance to my technicians so that I don't have to fly in an expert all the way every time there is a problem. You may call it something like autonomous maintenance, where you are, even with the skill level variance that you might have with your current technicians or operators in your factory floor, you are still generating personalized recommendations, personalized steps to follow according to their skill level, and you are filling up and enriching all the incomplete documentation that you may have in fixing equipment. So I really need to generate easy to follow documentation for my guys. So as you can see, there are challenges all the way, but this shows you how you can start from actual criticality analysis before the project even starts to, in the end, how to repair the equipment after we get the ML model set up. And there is different data required at each stage of this operation. At the start, I would need to know both structured and unstructured information. I need to know the machine information. I need to know things like percentage of breakdowns, percentage of planned work orders, percentage of unplanned work orders, what is the OE, how many equipment are there. All of this quantitative data I need. I also need to have some unstructured data here as well, like expert analysis or opinion on which machines to prioritize. And why both of these are important, let me give you an example. So I was doing a project for this large manufacturing organization, and we went in, and the general manager says to me that, Hamza, I have this bunch of equipment. Some are cutting machines, and then I have a packaging machine, and there's a specific motor in the cutting machine that always fails, and whenever it fails, we always have a big stoppage, and that is costing us a lot of money. So I talked to my maintenance leaders, and they're telling me, you just have to put sensors on this particular motor and tell me before it fails so that I can take action. So I said, okay. And I didn't do quantitative analysis at that point. I just relied on the expert opinion. We created the full roadmap. We created the whole scope. And then we found out that the amount of money that we're going to invest in actually doing this predictive maintenance program, it would be much easier to just replace the whole thing and cheaper. So this is very important, to do quantitative analysis. Then once we identify the correct equipment for the predictive maintenance program, we have to put in sensors. So here at this stage, you will be dealing with mostly structured data, time series, sensor data, and maybe some maintenance logs. Maintenance logs are important because even if you're getting time series data from the sensor, let's say you have a vibration sensor, the temperature sensor on the equipment, you're getting all of this data in, and you're seeing some anomalies. You really have to compare it with the previous maintenance logs and what kind of data was there before, so that you can recognize the pattern and figure out that maybe this failure happened before because of a maintenance that's been performed. So you need both of these. Then for stage number 3 and 4, we also have structured and unstructured data. So stage number 3, I need structured data related to my inventory information. Do I have spare parts for repair or replacement? What kind of failure the machine is experiencing, we'll get it from step number 2. And then on the unstructured side, we need machine manual, that is OEM SI provided. We need to extract the right info from there and put it in a template based on the old work orders. And then in the final stage, we actually need to use all the standard operating procedures and enrich them with the data that we are getting from the previous stage. So the data flows from stage 1 to 2 to 3 to 4, and at each stage, more and more data gets added, right? So what we're going to do now is going to build this 4-stage application using MongoDB Atlas and the technology that we offer. And you'll see step by step how it all comes together. So let's get started with stage number 1, machine prioritization. So as I mentioned, over the course of my career, I've done many such projects, even before joining MongoDB, where I went into a factory, I analyzed historical and current machine utilization rates and losses due to breakdowns or stoppages. And then I correlated my findings, quantitative findings, with the experience of the people on site who have been working on this equipment all their lives. And then I combined all this, correlated that, and provided some insight to the general manager on which machines to prioritize, and basically just create a roadmap for their maintenance excellence program. This was a very manual work. Sometimes I was unable to include the full context into the prioritization exercise. because I didn't have access to a lot of quantitative data sources. Even if I did, I need to manually correlate all of this information. And if I was not careful, the ROI of this project was affected. I also had to rely a lot on the institutional knowledge due to limited access to these quantitative data sources. So when ChatGPTs and LLMs blew up last year, I thought to myself that what if I built a tool which is like a Gen AI based machine prioritization tool that can actually reduce the time I personally was spending on these manual analysis, and additionally reduce the risk of investment for my clients. So to be able to make this Gen AI application, the first thing I needed was a data store that I can actually use to store my structured and unstructured data, so that I can perform semantic search on this data and feed the right context to the large language model so that it does not hallucinate and provides the right response based on my data, and that can result in positive business outcomes. It will reduce the manual time I'm spending on these analysis. It will also reduce the risk of investment for my client, and it will reduce the cost of implementation because I will do the right thing the first time, and that's what we all want, right? So what does the reference architecture look like? To start with, I will take the quantitative data such as overall equipment efficiencies, any machine breakdown frequency, number of planned work orders for breakdown, unplanned work orders. I'll take all of that structured data from various sources. I'll take unstructured data as well as PDF files on any expert analysis that I've recorded or interviews, and I will aggregate and operationalize all of the structured and unstructured data inside MongoDB. And unstructured data is vector embeddings. Then I will perform semantic search and provide the right context to the large language model. And this can be enabled through a application framework. You can use LangChain or any other of your favorite frameworks. But you connect to MongoDB Atlas, you perform the semantic search, you get the context, you feed the context to the large language model so that it can answer the question such as which machine should I prioritize and why. And the response of the AI application will be, you should prioritize M0001 or M0002 due to A, B, and C reasons. And that's pretty cool. So why MongoDB for this kind of implementation? MongoDB Atlas really streamlines a RAG implementation or retrieval augmented generation. Atlas will handle it for you all under the hood. Your app data, your metadata, your context data, and your vectors are all stored in the same place. And as your app evolves, your document model is inherently flexible, as you may know already. And it's great for storing structured and unstructured data. You can just add to the same collection as needed, vectorize it, and store the vectors alongside it. Once you store the data, we give you that capability to perform vector or semantic search on top of it. And the performance of search operations can be optimized using vector-optimized search nodes or dedicated search nodes. With MongoDB, it's just one query in just one technology, in one language, one infrastructure to manage and scale, and there's no data duplication. So ultimately, you have lower total cost of ownership. I get all the tools I need to build my fancy new AI application, right? So let's use all of these tools now. And I just generated some data. So there's some structured data on this slide here, which is showing like there's a bunch of machines from start to finish. I have some cutting machines, some milling machines. Doesn't matter, you don't need to understand what the machine does, but there are a bunch of machines that help fabricate a gear for a gearbox, for example. And there are data in there such as breakdown frequency, there is breakdown index, there is percentage of planned work orders, unplanned work orders. All of this info is recorded. I got it as structured information from a table. And then I have some unstructured data. I have old work orders in PDF files in the blue border, and I have an interview that I generated with maintenance manager, which is just getting opinion or analysis of based on their knowledge by working on these equipment for so long, that which machine they think should be prioritized. So some quantitative data, some structured, some unstructured data. So let's use this now. So using all of this data, what I did was I followed our architecture that I showed you before, put it into MongoDB Atlas, and I generated this application which I can ask question, which machine ID should be prioritized for maintenance and why? And what it will do is it will get the right context from the using vector search and give me this answer that the machine you should prioritize is milling machine with the machine ID of M001, and these are the reasons why. And it is taking all of this structured and unstructured data together. It knows that it's M001 because of the structured data. And it's looking at all these different data sources such as interviews, all of the old work orders, feeding in all of this information and giving you the right result. And that saves me a lot of time. That saves me a lot of energy. I don't have to do all of this criticality analysis manually. Now you can apply it on other industries as well. And that's not limited just for manufacturing. But any sort of risk assessment where you're dealing with both structured and unstructured data, you can apply the same pattern. Okay. So we know that we have to put sensors on the milling machine. And that brings me to step number 2, which is failure prediction. So what exactly is failure prediction? I know what my machine is. I'm going to put a data acquisition box or DAQ next to it. I'm going to install like non-invasive sensors on it, the vibration sensor, let's say for measuring tool wear, I can install temperature sensors. I can install all sorts of like current sensors so that I get a understanding of behavior of the machine as it's running, right? So after I install the sensor, I'm starting to get raw data from these. I'm going to pass them through Atlas Stream Processing, which is a new tool, and it was mentioned in the keynote. And we'll have talks here later today, which will go deep into Atlas Stream Processing. But what Atlas Stream Processing actually does, it enables processing streams of data before the data hits the database. So you can build aggregation pipelines in an Atlas Stream Processor to continuously operate on the streaming data that's coming in without any delays inherent to batch processing. You can perform continuous schema validation, and you can constantly publish results to MongoDB Atlas after doing your data transformation. And Atlas is where all of my sensor data will stay, and will give me that single view across the equipment. Then, once I have data inside Atlas, what I'll do is I have another application running in the background, which is connected to my MongoDB Atlas instance using change streams. So whenever a new data set lands inside Atlas, change streams run, my application gets notified, and it runs a trained ML model. I'm using a decision tree classifier. You can use random forest, you can use gradient boost, you can use any normal ML model to train on these type of sensor data. And then the model results are actually stored back into MongoDB using a MongoDB driver. So what is coming back in step number 5 is the actual failure information and root cause. Is the machine going to fail? If yes, then what is the impending failure? The tool wear, power failure, or any sort of other heat stain failure, and so on. Once I have the alert, I store the alerts back into MongoDB. And then I visualize them using Atlas charts. I also use Atlas device sync to sync the data or the alert to a user application. It can be a mobile app, it can be a tablet application, it can be a web application that is on the shop floor, and you can see a nice little dashboard with all the alerts. And if it's a mobile app, the user will get an alert immediately, and they can actually go and take a look at the equipment. So from raw data, time series data, all the way to actually syncing the alert back to the user, we provide you the full building blocks. So let's look at like how the data looks like. So we have the machine. This is an example data set that I generated. You'll see there are some temperature values. There is some values related to tool wear, but all the values are strings, right? What I'm going to do with Atlas Stream Processing is I'm going to transform this data so I get values in numbers and floats and integers. And then I put all of the sensor values in an object called data, and I added the machine ID. This is just an example. You can perform much more complex operations using Atlas Stream Processing. The point I'm trying to make is as your raw data flows in, you can actually transform the data before it actually hits the database. Now this transformed data is then stored inside MongoDB Atlas. And then I have an inference engine running that is relying on change streams to get the latest value in, run analysis, and let's say it detected a tool wear failure. So it will generate another document that I will store back into MongoDB Atlas database. At that point, I can have Atlas chart set up and point my Atlas chart instance to the failure collection, which is getting all the alerts. And I can show these neat charts on what kind of failure is happening, whether the failure or alert has been acknowledged or not by the operator, and total how many alerts we had in the past shift. I can also use the same workflow to send an alert down to a mobile app. You can see the alert will be like a toolware failure. You'll see the machine ID. I can send whatever data I want through this device sync process. It is pretty cool. It gives you bidirectional synchronization out of the box. So if you press on is acknowledged button inside your mobile app, it will send back that notification, and the document inside MongoDB Atlas will be updated. So it's not just one way, it's actually bidirectional. So now, let's see how this all looks like. So this is a data set that I got from Kaggle. It's a milling machine data set, and then you can see that I used the full data set to train a decision tree classifier, and this is just a sample data for my testing. You see that there are temperature values, there's tool wear, there's torque information, and so on for different type of product that the milling machine is running, right, at different timestamps. So I created a producer application, which is just a simple Node.js application that's reading the CSV file and then publishing the data on the top left. And just below that is Atlas Stream Processing. Atlas Stream Processing is taking all of that data and transforming it. And then Atlas Stream Processing is responsible for pushing all of the data into MongoDB Atlas. In the middle, what I'm doing is I'm showing you MongoDB Compass, which provides a nice UI to visualize data that's in MongoDB. And I have it open to a machine's failure collection, which will only get populated when my ML model detects a failure. So now it detected toolware failure, and at the same time I got an alert on my mobile app. It's very, very instant, and it works right out of the box. As I get more and more alerts, the failure collection gets populated, and my device syncs that failure information down to mobile apps. It can be more than one mobile app that you want to sync it to. So you can see from raw data, we transformed it a little, just to show an example. We are publishing not just raw data but in the storage, but also storing the failure information in the same database. And we are syncing the failures or alert about the failure down to the mobile apps. And I can set up Atlas chart as well and link it to the same database, and it will show me how many failures are there. Now Atlas chart does have a refresh cycle. It will refresh every minute. But the sync process is instantaneous, and you will see sync appear as soon as we have a new record added to the failures collection. You can see how the acknowledgement changes from one is acknowledged and the rest are unacknowledged. So one thing very important to know here is that I did not use generative AI in this step. I used normal machine learning, I used normal decision tree classifier, I did the things that how it's supposed to be. Generative AI is very powerful if you use it with the right use case. What I'm trying to say here is, although there's a lot of hype about Gen AI, don't go and start applying it every single use case. There are certain areas where normal machine learning, normal AI will solve your problem. So now we know instantly when a failure happens. So let's look at step number 3, which is repair plan generation. This is, in my experience, very, very manual process. Typically, it's still is a manual process in many organizations who may have a maintenance management system, but it's not connected to all the other data sources, and they have to manually collect the data and feed it in. So what you need to do at this step is, now you know that this particular machine is going to fail. You need to create a work order. That will contain the following things. Number 1, repair instruction. How do you fix a tool wear failure? How do you fix a power failure? You need to know the spare parts. For a tool wear, you just need a tool and you can replace it. You need to know the schedule. You need to know the resource availability. Who's going to change this tool? So a lot of this data is structured, especially spare parts needed, resource availability, and schedule information. Some of it is unstructured, such as the repair plan, because you need to generate step-by-step repair plan instructions, which you're going to get it from the OEM-provided machine manual. And that can be a bit of a hassle because those are typically very thick. And the people that you have on site, your day-to-day operators, may not have been trained on that manual. So you need to extract the right information and pass it to them in an easy-to-digest manner. So if you do all of this, if you generate this automated repair plan, then you'll get a lot of tangible business benefits. Remember, we'll always go back to what makes sense for your business. You will optimize your scheduling periods, you will have an optimal sort of maintenance execution strategy, and of course you will increase productivity because your folks are getting the right instructions on the right time. So maintenance work orders are typically generated inside a central maintenance management system. It's also called CMMS. And the CMS providers are also investing heavily on generative AI for generation and scheduling of these work orders. Now imagine that I want to generate a work order based on a very specific template. I have a factory, it's ABC gearboxes, and when I detect a failure, I have the specific template that I want to use to generate a repair plan or a work order, maintenance work order. So this will contain repair instructions, will contain schedules, spare parts needed, and resources. So repair instructions come from the manual. Let's say the failure was a tool wear failure. So we have to perform the tool change operation. So what I did was I took a milling machine manual from the internet and then old work orders which were in PDF files, I generated them for example's sake. And then what I did was I took all of these PDF files, I created chunks of these PDF files, passed them through an embedding model, generated vector embeddings out of this, which is just a series of numbers and arrays. And I stored them inside MongoDB Atlas in an embeddings collection. This we have seen before. You will attend many talks today that will talk about how you can do this flow. What's interesting is that I use the same database to store all my structured data as well. I have the failure type. Failure type, if you remember, we got it from the last step. We had a collection which was populating based on the failures detected. So I have that. I have the inventory info. I got it from an inventory management system. I have the resources info. I maybe got it from my HR management system. And now, once I have all of this data, then I can use it to extract the information I need using vector search and aggregation pipelines working together and feed that into a work order generator application, which is actually going to use large language model to generate the work order with the right template. It will know the template because it has vectors of the old work orders. It will know the repair plan because it has the machine manual. It will know the inventory and resource availability information because it has that structure information also coming in. So in this template, first it will generate the template. It will add some blanks in there. It will fill in the inventory and resource info on the work order using aggregations, and finally generate the repair plan based on the machine manual. And this is what the final outcome can look like. From the start, we have machine ID, we have repair instruction, we have all the inventory information. And this whole setup can work inside your maintenance management system or outside it, depending on your setup. So we have a repair plan now. So what's the last step here? How can we use generative AI to enhance the operator or technician guidance instead of just giving them the instructions from a machine manual that hasn't been updated in a while and just ask them to go fix it? How can we help them better? So I'll take an example scenario here. So we are at a stage where we have generated the repair plan, right? It has some list of instructions. So now the central maintenance management system or someone detects that we have some service nodes sitting in another data silo that were uploaded to the platform by another technician in another country or even in the same country, but they are written in a different language. So let's say, for example's sake, we found these service nodes about fixing the same failure, but they are written in Spanish. So I can use the RAG architecture again here to intelligently merge these service nodes written in a different language with the repair instruction I generated in the previous step. Of course, first thing I need to do is extract the text from this PDF. And then I use a translation model to actually translate them into English because my other repair plan is in English. If my other repair plan was in Spanish, I would have just used it as is. Then I will use the original repair plan that we generated in the previous step, and I'll use the service nodes, and I will feed them back into a repair instruction generator app. And what this will do is it will intelligently merge these two and give me back an updated plan. And I can sync this updated repair plan using the same Atlas device-sync to the technician or any on-site support that I have. So how does this whole look like, step 3 and 4? Let's run through these. So in this video, on the left-hand side, I have a repair plan generator. On the right-hand side, which is right or left, depending on how you look at it, on the right-hand side, you have repair plan enhancer. So I'll ask a question, generate me a repair plan for a tool wear failure using machine manual and the old work orders. And for simplicity's sake, I only show you the steps on fixing the machine. And it's getting all of that directly from the manual. If we scroll down here, you'll see the data sources. Different pages of the machine manual were used. Different work orders were used to generate all of this, right? Now, I want to enhance it. Because over time, machine condition has changed. I found some service notes. I use some service notes written in Spanish. And I don't read Spanish, so I need to translate them and merge them with my original repair plan. So using the architecture that I showed you, I press on this button, it will translate them first and intelligently merge them, and you'll see now the repair plan or the step-by-step instruction is enhanced. Now we have more points, now we have more details, now we have the experience coming from the technicians into the picture, and that's how you keep on improving. That's what continuous improvement is. That's how you implement it using GenAI. You can see specific things like use soft materials to actually stop the debris. You can see things like how do you test it after changing the tool. So all of this institutional knowledge needs to be merged with the instructions provided by the OEM, and that is pretty cool. So let's bring everything together now. What we are doing is essentially chaining the AI, ML, GenAI applications in order to achieve an end-to-end predictive maintenance strategy. Our input was a mix of structured and unstructured data. We use all the neat services provided by MongoDB Atlas Developer Data Platform, such as vector search, stream processing, device sync, and of course, the database and the aggregation itself. These features enable us to provide the right context to the LLM and the right data to your AI model. And LangChain is used as a framework in this application, and I used some OpenAI models. You can use any model you want, and some inference models that I created using Python scikit-learn libraries. Finally, we get the desired outcome in each state, starting from which machine I want to choose, to what is the failure type. Failure type flows into step number 3, I get a repair plan. Repair plan gets fed into step number 4, I get the repair instructions. If you want to take one point out of my talk today, it is that you need to intelligently position GenAI with your existing ML and AI applications. That's how you can bring value to your projects and to your clients. And here, if you look at step number 2, we didn't use any GenAI, but we used GenAI before that and after that, and that's how we created the full solution here. At some point during this exercise, when I was creating these demos, I thought, why not use text-to-image models to generate some helpful like infographics from the manual text, and then I can generate some helpful diagrams for the operators to guide them when they're fixing the machine. So I tried a lot of prompt engineering, but the results were like so funny and weird that I thought I'll share it here. So I really failed at doing it. But this was the first result without any prompt. I asked the model, give me operator process of how to change the tool, and look at the hand there, where it's coming from. And then I said, okay, I'll start providing more and more context from the machine manual. So I copied out the lines and start feeding in it, and this was the second result, which was even funnier. There's this weird thing going into the panel. And then finally I had this, and I gave up after this, after I see hammer and spanner and their 4 hands trying to change the tool. So if you are in the audience, you're working on something like this, I would love to learn from you. And I'm sure with much more fine-tuning, we can reach somewhere acceptable, but we still have some ways to go, right? So in conclusion, we do understand that advancements in AI is transforming maintenance, and that has the potential to reduce maintenance costs and increase productivity. We know that some such complicated applications can be enabled using MongoDB Atlas Developer Data Platform, and we can give you tangible benefits. So let us talk and see how we can work together to achieve your vision. I'm here all day, love to connect with you and talk with you. I want to thank you for your time, and if you haven't done already, please take a minute to give me feedback on the survey app. Thank you so much.